Hello.
Hello, hi sir. Good morning. Bharat from NPTL, sir.
So who is it Naveen?
Bharat, sir.
Bharat. So how are you, Bharat?
Fine, sir. What about you, sir?
Fine, fantastic. So I
Yes, sir.
think who have all joined. Wilson has joined.
He left, sir.
Okay, fine. Let's see. We'll wait for some participants to join.
Yes,
It will
sir.
be too early, and then we'll take a decision.
Okay, sir.
So I think one person by name Pramod has joined. Hello, Pramod. Hello, Mr. Pramod. Are you hearing us? Mr. Pramod, you have any questions to ask? Yeah, please ask if you have any questions, please. Any doubts, any clarifications? Okay, you have no doubts? Okay.
Sandeep hasn't joined today. So I can't hear you.
Your voice is not audible, sir.
Now?
Yes, come here. Yes, I can hear.
I was muting because I was talking to somebody. Okay.
Sandeep hasn't joined today.
I think so. Yeah, maybe he has got some other work.
Okay.
Is all right. Pramod, you can ask. There is
One
one
more.
participant by name Pramod. Pramod Mali is also there, another participant. There are two Pramods. Do you have any clarifications, please? Okay, let us know how you are enjoying this course. Are you liking this?
Yes, sir. Yes, sir.
If something is not clear to you when it is being explained, please let us know so that we can get it clarified now.
Yes, sure, sir. Hello.
Tell me.
Yes, sir. In APT, this attached proton test and amide proton test. What is the difference in this
Okay.
two terms?
Yeah. Attached proton test is a test where you are going to do by applying certain delay between the two pulses. We will ensure that the magnetization for the protons, for example, carbons which are attached to one proton, or two protons, or three protons, or no proton at all, then they will evolve in a different way. That depends upon, did I explain to you diagrammatically? I'll show you 1 minute.
Yes, sir.
I'll see here, Pramod, look at it. What we are planning to do is in this experiment, we do an experiment like this. Okay.
Yes.
This is a 90, 180-degree pulse. Of course, these things I have discussed. This is called a delay, TD. Okay. This delay, we can control it. We can vary this delay. What happens if you vary this delay? When you have a different carbons, how it is going to be evolved? See, these are all magnetization vectors. The vectors start moving. When they start moving, how much it moves with a time delay depends upon the strength of the coupling and also the angle at which how much it has moved. For example, angle up to which it is going to be moving for any vector is given by an equation called theta is equal to pi into TD into JCH. JCH is the coupling between carbon and proton. This is clear for you. Now, let us see what are the coupling between CH proton, CH2 and CH3 protons. Look at it. In the CH case, you are going to get a doublet.
Hello, sir.
Yeah.
I'm not able to see the slides.
You're not able to see?
Yes.
Wait. Oh, I have to share it. Wait,
Yes,
wait. I have not shared it. Wait a minute. I'll share it now. Okay. Are you able to see it now?
Yes, sir.
See, what I was trying to tell you is we can modulate how the vectors, coupled vectors between carbon and proton vary. That depends upon different carbons. It could be quaternary carbon, CH carbon, CH2 and CH3 carbon. But This depends upon the splitting pattern. For example, how much it moves each vector is given by this equation. I told you in this the pulse sequence, I told you there is a delay here. This is the time which is of the order of few milliseconds. During this time, the vectors will start moving. How much it moves is given by this equation. Okay.
Yes.
For example, if you consider a CH vector, the center of this doublet is the chemical shift. And CH is going to be a doublet because it is coupled to proton. So there is, if you measure from the center, this will be half of the coupling, and this is another half of the coupling. In NMR jargon, we say one of the vector is moving faster, other vector is moving slower from the particular axis. See, after applying 90-degree pulse, you bring the magnetization to a particular axis, then one will move in one direction, other will move in the other direction, which is called fast moving and slow moving vectors. What happens if I consider CH2? Same thing, but only thing is the central peak is exactly the chemical shift. This is also in NMR jargon, we say this peak will be always on resonance. In the sense, it will be fixed to a particular axis when you bring it in. This will not move at all, this vector. Only these two vectors start moving. Again, one moves faster, one moves slower. But can you see the difference here? This separation is half the coupling, whereas this separation is full coupling, J coupling. This clearly also tells you whatever happens for half the coupling period for CH coupling, or let us say full coupling for CH2 will happen for half the coupling for CH doublet. What happens if you go to the CH3? Identical. But CH3 has, wait a minute, a triplet quartet like this, 1, 3, 3, 1. Again, from center is the chemical shift. And these two vectors behave exactly like CH proton. But remember, last two, these single peaks, this one and this one is also separated by 3J/2. Exactly, whatever happens here, let us say if it rotates by 90 degree, these two vectors move 3 times faster. So if it moves by 90 degree, this would have moved by 270 degree. Essentially, these CH3 protons, these vectors behave identical to CH proton. Only for CH2 it behaves different, which I explained to you in the diagram. Here, for example, at particular delay, half the coupling, then what will happen? The vectors move by 90 degree. So that means you bring the magnetization to x-axis. Actually, you have to see in the 3-dimension. It is not vertical, they are horizontal. When it brings the x-axis, it starts rotating like this. One moves like this, one moves like this by 90 degree. Okay, each spin vector rotates by 90 degree and they're exactly anti-phase. This is called anti-phase character in NMR. They are opposite to each other. Imagine this is a 3-dimensional figure. I could not write 3-dimension, but I'm showing in 2-dimension. But from z-axis, it came to x and start moving with this. Okay, this is what is happening. So when you add up these two, what will happen? It is a vector addition. You know about mathematics. In the vectors, we can add up which are in opposite directions, equal and opposite magnitude. The sum is 0. Exactly, at exactly half the J coupling, these two vectors are opposite in phase. So if you add up, the signal will be 0. You will not see any signal at all. Same thing if you do it, for example, let's say I'll show you. These are, you don't need to see these things. Just remember, at half the coupling, the signal is 0. If you wait for one full coupling, then what will happen? They will start moving further, and exactly after one coupling, the signal becomes negative. You understand? In the case of CH,
Yes.
At half the coupling, signal is 0. At one coupling, if you take 1 over j of the value of the TD, they would have signal moved completely by double this value, double the speed. Automatically, where it is positive, here it becomes negative. At exactly half j, it is 0. Okay. This is what happens. I calculated it by some mathematics. You don't worry about those equations. Whereas if you come to CH2, what happens? I told you, central peak will not move. And this is double the value of this one. If this separation is half the j, this separation is 1 j. Obviously, you can understand what is going to happen for whatever happens for half j, for CH will happen for full j here. Okay. You see here, at exactly in this case, at 1 over j, instead of negative, this becomes positive. Go for other one, CH3. CH3 has 4 vectors. 2 are fast moving, 2 are slow moving. And again, you see that one component is moving 3 times faster. Doesn't matter. But finally, both 2 fast moving components and 2 slow moving components behaves exactly like CH carbon. And they also, it takes more time to explain. Remember, it behaves exactly like CH carbon. In CH also we saw this, at 1 over 2j it was 0, at 1 over j it was negative. Exactly what happens for CH3 carbon. All right. So you remember, see this one, what I have written, a half j, all these carbons will have 0 intensity, but 1 over j, this is negative, CH is negative, CH3 is negative, CH2 is positive. What is the use of this? The use of this is you can vary this time delay and identify based on whether the signal is positive or negative. You can find out whether the carbon has attached odd protons or even number of protons. And this is what is called attached proton test. And you can see diagrammatically I have shown here how the intensity changes here. For CH2 and CH3, whatever, I'm sorry, this is wrong. This should be CH3. I have made a mistake. This is CH3. CH and CH3 behaves identical and opposite what that of CH2. Are you with me, Pramod?
Yes, sir. Yes, sir.
You understood? Attached
Yes, sir.
proton test means it is a test to identify the carbons in a crowded region. You can take a decoupled carbon-13 spectrum. There will be lots of carbons. But how do you find out which carbon is CH, which is CH2, and which is CH3? Then you will not know. There is another way to do that by using what is called a off-resonance decoupling. You have to see the coupled spectrum, etc. But at the same time, if you want to do the decoupling, simplify the spectrum, also identify which is CH, which is CH2 and which is CH3, this experiment is done. It is called attached proton test. Am I making sense to you?
Yes, sir.
Okay, anything else?
Then what is amide proton test?
I'm sorry?
Amide proton test.
Amide proton test, I didn't say. This is for carbon proton. If you
Oh,
can design the same thing for any 2 heteronuclei, like this
yes.
is carbon and proton. You can do it for nitrogen proton also.
Yes, yes, got it, sir.
But where do you come across NH2, NH3, NH4? You don't get it, NH3 you will get it in a molecule. Generally, NH and NH2 you will get.
So,
I
yes.
don't know. I have not seen the molecule which NH3. See, whatever happen, you experiment you design for heteronucleic carbon and proton, you can also design for other heteronucleic nitrogen and proton also.
Yes.
It's okay.
Yes, yes, sir. Thank you.
Oh, Sandeep has joined. How are you, Sandeep?
I'm good, sir. How are you?
Fine. Anybody else? Renu has joined. Renu, are you there? You have any doubts? Any doubt? Renu logged. Renu, yeah, you have asked, raise the question. Raise the hand. Tell me, what is your doubt?
I think she, by mistake, she has raised the hand
Okay.
and left. Close video off and audio also off.
I don't know. Renu, are you listening to us? Are you hearing what me and Sandeep are talking? Okay, maybe she doesn't want to interact.
Two Pramod are there. Pramod Mali, another Pramod.
Yeah, one Pramod was talking to me.
Yes, sir, I am same.
Okay,
Oh, you are
same.
same.
Yeah, I
Okay.
joined with phone also. So on my laptop, I am not able to talk. So I joined with
Okay,
laptop
Okay,
and
fine.
okay,
mobile.
okay, okay, okay.
Renu, you have any doubts?
No, sir, I have no doubt.
Oh, very good. So everything is clear for you.
Yes, sir. Sir, I want about final exam.
What do you want to know?
Sir, what is the whole syllabus?
No, madam, what we are going to do, there is a formula given by NPTEL, according to which about 60% or something, there is a formula of the questions are from the PPTs, PowerPoints.
Okay, sir.
Whatever the PowerPoint I have been using, if you
Yes,
have
sir.
seen the videos, whatever is given, that's we have to ask. That is one of the conditions. And then
Okay, sir.
remaining 30% or 40%, I think, some formula is there, are from our assignments.
Okay, sir. All
And
questions will be option type.
I'm sorry.
Optional questions will be there, sir.
Yes, everything is objective type. Each question will have 4 answers. 1 may be correct, 2 may be correct, or 3 may be correct, or all may be correct. And you
Okay,
have
sir.
to mark which is correct. That's all.
Okay, sir.
And the questions will be taken from the PowerPoint slides also. Exactly what is shown. About 60%, 25 to 30% from the assignment. Remaining 10% or 20% is general, where we can ask the question where you have to think and answer.
Yes, sir. From NMR or
Of
Oh,
course,
yeah,
it
spectroscopy.
yeah,
is
yeah,
only
yeah.
NMR course. We cannot ask you something which we don't know. We can
Okay,
ask you
sir.
only what we know.
Yes, sir. Thank you so much, sir.
Thank you. So are you enjoying the course?
Yeah, sir.
Yes, sir.
You have submitted all the assignments?
Sir, I have completed 8 weeks.
Fantastic. 8 only we have done. Only 9th and 10th we are doing now, I think. Yesterday,
Yes, sir.
what happened, Wilson, Sandeep, that issue was resolved?
Yeah, I need to check it, sir.
Hmm.
Actually, I saw that something was wrong into that. So
Loading
Wilson
was not
sir,
correct.
Wilson sir actually uploaded that.
Hmm.
So I tried to correct, but it was not allowing me
You
because
ask our NPTEL office, they won't.
so as it is
Bharat is
once it
there,
is
you can ask
uploaded,
him.
it cannot be deleted actually.
I see.
So now let's see what is the
Ask
solution
Bharat
for
who is
that.
there, NPTEL person, or even talk to Maya.
Maya, I will talk.
Hmm. Okay,
Otherwise,
another question.
Bharat, do you know can we delete the our this assignment? Suppose it is uploaded wrongly.
I don't know about that, sir. I want to ask Maya.
Okay, okay, okay.
Okay, you can ask Maya, I think. So one person by another person has joined one with a mobile OnePlus CPH2 467. I don't know who is that person. Can you please identify yourself?
Yes, sir. This is Sandeep Pawar, sir.
Sandeep.
Yes, sir.
Okay, Sandeep, please tell me. What you have any clarifications, any doubts?
Uh, That's sir. I wanted the interpretation is my issue there because I'm not subjected to this one NMR. So just I will
Okay.
learn and then, okay, I will learn and then do this.
That's fine. You can learn, but interpretation is a very, very broad statement. Interpretation of 1D, 2D, varieties of 2D experiments, varieties of 1D experiments, heteronuclear, which nuclei, spectra, everything. You have to be very specific. If you have any particular doubt, I can right now show one or two simple example. Shall I show you one or two simple example?
Sir, can you please proceed for this for any a few example for the simple molecule? So I get
Okay, please be there. Right now, I'll show you one or two simple spectra. Okay.
okay, sir.
Okay. I'm going to share the file, which I made it just this week for giving the lectures at okay. See here, I'll show you some of the simple first order spectra, which is made for the pharmacy students, which I'm giving a course tomorrow at the pharmacy college. Only for them, I made just last week. I'll show you the spectra. You can closely follow. If you have any doubts, you can interrupt me.
Okay, sir.
Okay. Hello, are you with me?
Yes, sir. Yes, sir.
Okay. I'll take a simple example of this molecule. First, I will
Okay.
show you 500 megahertz spectrum, and this is the molecular formula. There are two ways of doing. If you give me spectrum, I don't know the structure, but I can get the structure also. Or, since it is the interpretation is the problem, because for pharmacy student, the simple way I wanted to explain, I assume that I know the structure, and I will try to interpret the spectrum. That's what I'm going to do right now. Okay.
Okay.
And this is the molecule. And what I have written here is the chemical shifts, different chemical shifts for this proton, this CH2, CH2, CH3, etc. Okay. This is the molecular structure. I know. If you don't give me this also, still I can get the structure from the spectrum.
Okay, sir.
Right now, this is the spectrum I'm showing you. See, each of this group is expanded here. This is a triplet in one color. This green color is a sort of a sextet. And this one is a triplet of doublets. This is a triplet. Now, I'll ask you the question. Of course, I will answer it just for your interest. How do we go ahead in interpreting each of these peaks? This we have to make what is called assignment. Assignment means we have to assign each peak for a particular proton. How do we do that? First thing, you have to be very, very careful. You should know where the chemical shifts are coming, and all the integral intensities I have given here. 1, this is 2, 2, 3, like that, approximately. But I assume these are all computer calculated.
Uh,
Then I round it off to a
Renu.
nearby value.
Renu,
जी sir.
are you telling something?
Then
Hello?
you have any doubt, madam?
So, if you have doubt, okay, ठीक है. उसका mic on. She left the mic on, so it was disturbing.
Okay,
actually.
okay, no problem.
Now
So
she has stopped. Okay,
Okay,
she has muted.
see, I'm showing you there is a triplet here. I have always we find out integral intensity. I mean, this is a simple thing. And this, I know it's 3 intensity. This is 2 intensity. This is 2 intensity. This is 1 intensity peak. We have expanded here for your purpose. By chemical shift, I know peak comes here at the high field. We call this as high field region. are usually CH3 peak. So I will guess this is a CH3 peak. I don't know whether it's right or wrong, but we'll see that. If this is CH3, you can really see from the structure, this is coupled to, this is sitting next to CH2. And these CH2 protons and these three CH3 protons, there is an interaction called J coupling. Because of that, this CH3 proton will be a triplet because of two equivalent protons. And I will safely say this is a triplet because of CH and this CH3. You may ask me a question, what about this one? This is also a triplet. There are two ways to solve this problem. One, by chemical shift. It is very, very low field, that is downfield. So it must be the
Aldehyd.
proton which is attached to or close to some electronegative atom. So I guess this must be CHO. Okay. So I would say this is CH3 and this triplet is not CH3. We'll come to that later. What is the CH3? I would say this CH3, this triplet is a CHO proton. Why it is a CHO proton? Because remember, this proton is coupled to these CH2 protons. Because of this two equivalent protons, this will become a triplet. This is triplet, and also because of chemical shift being downfield, I would safely say this is CHO. Are you okay with me?
Yes, sir.
Now what are the remaining two peaks I have to assign? What I'm going to do is I will say this is CH2. Why it is CH2? Because and also which CH2? That is another thing which we have to see. I would say this is this CH2. Why? Because this is coupled to these two protons and becomes a triplet like this. And each line of the triplet is split into a doublet because of this proton. And you can find out this separation and this separation should be identical. That's why I safely say this colored CH2 is nothing but this CH2. I can interpret it. Then this is called triplet of doublet. What about this one? Next one. I would say it is CH2. Why do I say it is CH2? This CH2. Remember, this CH2 is coupled to the CH3 protons. I have explained to you during this multiplicity pattern in the beginning of the course. Because of this equivalent protons, chemically equivalent, this will become a quartet. And it goes by Pascal triangle intensity 1, 3, 3, 1. And each line of the quartet is further split because of this CH2. There are 4 lines, 1, 3, 3, 1 intensity. Each line is a triplet. And sometimes if the couplings are almost close by, need not be exactly same, something which is close, which we cannot resolve, some of them will overlap and gives us a pattern like this. And I would say this CH2 is this one. Now we can interpret the multiplicity pattern. I would say this is a triplet because of this CH2, and this is a triplet because of this CH2, and this is a triplet of doublet because of this and this. And whereas this one is a quartet of triplets, it is also called pseudo sextet. Are you with me, Pramod? Hello?
Yes, sir. Yes, sir.
You have any doubt in this?
No, sir.
Okay. I'll give you a simple example of this spectrum. Another one.
Sir, can I ask one question?
Please ask.
Sir, here is mentioned as the CDCl3, the solvent is there. Sometimes DMSO we also use. So, which is a better solvent for NMR?
Okay. That depends upon your sample molecule.
Okay.
All are not soluble in all the. There is no universal solvent to say everything will dissolve in a particular solvent. Some dissolve in polar solvents, like DMSO, and some will dissolve in water, like amino acids and others. They will dissolve in water. So depending upon solubility of your sample in a particular solvent.
Okay.
And we have to use deuterated solvent of that. Are you with
Okay.
me?
Yes, sir.
Okay. Now are you comfortable? I'll give you another simple example of this molecule.
Okay.
Now, this is the structure I have given you, and this is a simple spectrum. I'm showing you a very simple spectrum. I'm sorry, it is not post, it is a substrate. See, only yesterday I was making it for tomorrow's course. So if I have made a mistake here, it is so subscript. So now I have put different colors here. Ca3 is this color, and CH2 is this color, red color, and this is green color, and this one is this color. I'm sorry. This is this green, and this is CH2 is red. This should have been red anyway. So now can we interpret this one very easily? How do we interpret this? Look at this one. These CH2 and CH3 are far away from any of these two protons, CH3 and CH protons. 1, 2, 3, 4, 5 bonds away. And this is maybe 6 or 7 bonds away. So we can safely assume these protons are not coupled to these protons. So it is an isolated group. In which case, this will become a triplet because of this, and this will become a quartet because of this. I can see one triplet here and one quartet here. And this triplet is the CH3 becoming triplet because of this. This CH2 is a quartet because of this CH3. Now we'll go further. I have assigned, this is one this CH2 and this CH3 we have assigned. Now I have this CH3 and this CH. This group also I have to assign. These two CH3s are equal, chemically equivalent. And what happened? This will couple to this proton and becomes a doublet. So it is a two-line pattern of high intensity, you see. This is a doublet because the CH3 is coupled to the CH proton. Then what about this CH proton? This CH proton is coupled to two CH3s of equal strength because they are equivalent. So it is going to give a pattern like this, which is called a septet. Because why do you get a septet? This proton first becomes a quartet because of this, and each line of the quartet is further becoming quartet because of another CH3. And you can see how we get a quartet. I have written like this. First there is a quartet, and each line of the quartet is becoming another quartet, 1, 3, 3, 1 like this. And finally you add up the intensity, you will get a septet pattern. This is how it comes. Okay. I hope you are okay with me, right?
Yes, sir.
I will give you another simple example of a molecule like this. This is, in fact, I don't know if you are in Bangalore, you come to Pharmacy College, KLE College of Pharmacy tomorrow. I am giving full day course. I'll teach 1D, 2D interpretation, everything for the benefit of chemistry student. No mathematics, only interpretation.
Okay, sir. Can you
Bangalore, doesn't matter.
sir?
Hmm.
One question I have here. Can you give us the example of the isomeric compounds? So compound having
Exactly.
the same.
That's what I'm trying to show now.
Okay, sir. Okay.
Okay. This is the example because, for the drug in the pharmacy college, they make drugs and they always worry about isomers, enantiomers, etc. That's
So
why
they
for
are
them I'm showing this example.
sometimes single compound having the two isomer and two diastereomer.
Exactly, sir. You are right. I will show you that now. In
Okay.
a simple example, of course, there are many experiments we can do 1D and 2D, but this one I want to show because they're all BSc and MSc pharma students, they don't know much NMR. Making it simple for them, I am taking this molecule and this is the spectrum. I'm getting it. Now my question is how to make the assignment. And I know the integral areas. This is 2, 2, 2 and 3. Because this is 3 intensity, 2 intensity, 2 intensity, and 2 intensity. So that means this is a CH2, CH2, and some H2 and Ca3. I know there are 3 plus 6, 11 protons are there. No, 9 protons are there. This matches with my formula. Now, how do we interpret it? I know if I have a 3 protons, 9 protons, 3 carbons and nitrogen. There are various possibilities we can think of. It could be this conformer, or it could be this the structure. Either it could be this. These are all different possible structures. Can this be the structure of this molecule? If you look at the spectrum, I would say wrong, because that all the CA3s are chemically equivalent. It gives a single peak. But in my spectrum, I am getting 4 peaks. So I would say this is not the isomer. What about this one? This could be the one. But here again, you have 3 peaks only. These two are identical, this and this. But we have got 4 peaks. So this is also not correct. Come to this one. Of
So
course,
here,
all four-
NH2,
I'm
sir,
sorry.
here, sir, here, when NH2 proton can interact with the carbon proton.
Yes, carbon proton coupling is there, but I'm not showing all those things. I'm showing only proton spectrum.
Okay, sir. Okay.
There is another possibility. This also is there. This also is there. For example, this also gives 4 peaks. But the intensity ratio is 1, 2, 3, and 3. This is not possible because what I have got the intensity is 2, 2, 2, 3. So I would say this is my structure. Now, to confirm that, we'll go and look at the multiplicity pattern. I would say this is a CH2 proton with a red color, and this is a triplet. And this is a CH3. This CH3 is also a triplet because of this. And this is NH2. And I would say this is CH2. Again, this CH2 is coupled to CH2 and CH3. And it gives rise to a complex multiplicity pattern. Of course, we can get this, what is this and everything. It's a triplet, and each line of the triplet is a quartet. And you are going to get finally a septet, a sextet like this. Here somehow accidentally the couplings are equal here. Now you may ask me a question, what about these NH2 protons? Why it is not split by CH2? Then there is a various explanation for this. There are 2 possible conformers for this molecule. I mean 2 magnetic orientations of the NH2 proton. It could be like this or it could be like this. And what is happening? There is a Brownian motion is going on. There is 50% of the molecules with NH2 like this, and 50% of the molecules with NH2 like this. And they keep coming closer and move away. Because of the Brownian motion, it comes like this. When it comes like this, then it forms a hydrogen, forms a bond like this. Temporarily, it creates a bond like this. And after some time, but still magnetic orientation is not changing, but it establishes contacts with other proton. This nitrogen establishes contact with the proton of the other molecule. I mean, do more details, I'm not telling you. You can see that. This is what is called chemical exchange. And finally, 2 molecules again get separated. That is not final. It keeps coming and going, keeps coming and going. Keeps on happening forever. As a consequence, this is in NMR jargon, we call it as self-decoupling. So NH2 will not be seen as it is coupled to CH2. Are you okay with me?
Yes, sir.
Okay, I wanted to show you another example of a isomer. I'll show you this. This is not needed. This is also not needed. Here. You asked me about isomer, you know.
Yes, sir.
This is identification of 2 isomers. How do I identify 2 isomers? Very simple molecule I'm taking. And this is the 2 spectra. Very simple spectra. One is CH3, one is, there is a triplet, a quartet, and a singlet. That's all. Here also triplet, quartet, and a singlet. But there are 2 different molecules, 2 different isomers. I can even get the structure without even you telling me. But for the sake of presently, you assume I know the structure. I make the assignments. I know what are the possible structure. One is this, one is this. You see, these are isomers. Here, C double bond O is here and O is here. Whereas in this case, OCH3 is here and C double bond O is here. So, small change is there in the possible structures. But if there are three ways to resolve this. One, you look for we have to do a two-dimensional experiment to trace the carbon skeleton of the molecule. For example, in this case, 3 carbons are in a row. If I know, I can trace from this carbon to this, and I can go from this to this. So inadequate will show me these 3 are coupled. One way. Other way, I can see for carbon-carbon couplings in the carbon spectrum. That's one way. I can theoretically calculate chemical shifts. That's another possibility by using what are called Schulleri rules. I am not going to tell you that. You will listen to my first course in which I explained in detail about Schulleri rules. Now, before going further, I will tell you how do we get the spectrum when 2 carbons are coupled like this. Remember, carbon 30 is 1% abundant. This carbon is 1% abundance. The probability of both the carbons simultaneously to be as carbon 13 is 1 in 10,000, 0.0001 possibility. So, but nevertheless, if I see the coupling, each carbon will be a doublet. This will be a doublet because of this. This will be a doublet because of this. Because of 1 bond carbon-carbon coupling. We'll see what happens. There are 3 carbons like this. Now, this is what we'll see when 2 carbons are there. Both carbon 12, no signal. When this is carbon 13, you get 1 peak. When this is carbon 13, you'll get 1 peak. When both are carbon 13, you get 1 peak for both, but small chota lines because of coupling. This is the spectrum you are going to get. Now, what happens if there are 3 carbons in a row? Consider all the 3 carbons are in carbon 13 state. When this is carbon 13, you get 1 peak. When this is carbon 13, you get 1 peak. When this is carbon 13, you get 1 peak. But now, this is the situation. Possibility of all the 3 being carbon 13 is 1 in a million. Remember, it's very, very difficult. Still assume I will see that. I am a very careful experiment I'll do, and then I still see the coupling. In which case, if I see this carbon coupled to this, exactly I showed you when 2 carbons are present simultaneously, you get this pattern. What about these 2 carbons together? When this and this are coupled, you get this pattern. And I'm assuming this coupling and this coupling and this coupling are different. You see the separations are different here. Now, simultaneously, all the 3 are present. I get a pattern like this. Only for this carbon, it is coupled to this, and this, you will get 2 doublets. For other carbons, you get only single doublets. You see the difference? Now, in reality, this is the spectrum I must see. Now, let us go back and record the carbon 13. Don't worry about that. Carbon 13 NMR spectrum. Look at it here. Here, 1 doublet. Here, 1 doublet. And here you see, this carbon has 2 doublets. Obviously, I would say this is this carbon. It is coupled to this and this. 2 carbon 13 doublet satellites you are seeing. This is called carbon 13 satellites in the carbon 13 spectrum. Whereas, here and here you get only 1 doublet. Come to this one. You have 4 different doublets because none of the, only this will become a doublet, this will become a doublet, this is a doublet, and this is a doublet. So I can identify from a simple 1-dimensional carbon spectrum whether it is this isomer or this isomer. Mind you, it's a very, very time-consuming experiment. Don't try to do that. If you go to any NMR lab and say, I want 1 day time to do this experiment, they will not give you. You have to do a different experiment. But for showing purpose, I'm explaining how we can resolve this. Are you with me?
Yes, sir. Yes, sir.
Did you understand?
Yes, sir.
Okay. So
And
I
sir,
just
same-
wanted to, tell me please.
Sir, and same thing applied for the if molecule having the two chiral center, only that
That's also possible, sir. Chiral center, one
Yes.
problem is NMR will not distinguish enantiomers.
Okay.
For enantiomers, NMR is blind. Let us say you are a chemist, you make pure enantiopure R and enantiopure S. Without
Okay.
telling me you record a spectrum independently and show me, I will not be able to distinguish.
Okay.
Spectrum will be identical for both.
Uh,
But there is a way to do that.
is there possibility for J coupling value is different, slightly
That
different
also
for
same, sir. That is also not different. But
uh,
there is a way. You can convert enantiomers to diastereomers and then identify.
sir, how it is possible, sir?
Okay, I am not a chemist. We'll see our Sandeep is going to answer. Sandeep, can you please tell him how do you
Yeah,
convert enantiomer to
actually,
diastereomer?
yes, sir.
1 second. Shall I stop the sharing this? Are you okay with this?
Yes, sir.
Yes, sir.
Stop.
Yes, sir.
Okay, thank you. Now Sandeep will explain to you.
See, the thing is, converting enantiomer to diastereomer, there are several ways. So one is either you can derivatize. If suppose you have a functional group which is reactive, so add another known enantiomer which can react with that functional group, and then you will form a diastereomer with the two
Okay.
chiral centers. Okay.
Okay, I understood. Okay.
And other thing is, if it is not soluble, not reactive groups, only groups they can interact with some hydrogen bonding or other weak interactions. So there are called solvatizing agents. So you add those. If they interact even through hydrogen bonds, they generate the diastereomerism into that molecules. So that can distinguish. If that is also not possible, then there are some called chiral media. That is some liquid crystals, means low order aligning order parameters, low order parameters having some semi-solids like say liquid crystals. If you dissolve into that, if they are chiral, so they try to embed into that in the fashion, suppose R will try to align with another fashion and S will align with another fashion. So that also generates a pseudo diastereomerism into the enantiomers, and those can be distinguished.
Okay. Okay.
Huh.
Okay, I understood. But instead of this NMR, is there other technique like XRD, single crystal
The
XRD?
XRD don't helps, but you can do this, and you cannot crystallize all those molecules. But
Okay.
HPLC works.
Yeah, HPLC is there, but we cannot say that because in HPLC in reverse normal phase, isomers are separated. In reverse phase, enantiomer also separate. No issue for that one. But we don't know actually which isomer is coming at which RT. So that's why we are differentiating this one. So
Which
we are
one is
interested in
that? Which one is which? That is a different thing in NMR also. You can
yeah.
distinguish. Then also which is which, like yes is or yes or yes.
He
Then
asking
you
for
have to
absolute configuration.
you have to do analysis for absolute configuration.
Yes.
Okay.
So that is the different. Like it is also the same thing, but if you have to compare with the known ones. It is a shifting right side or with the in presence of suppose it is R. So R with R in an R your chiral media shifting right or left, depending on that you can just assign. With known, then you can compare to the unknown.
Yes. Okay, sir. Okay, I understood.
So there are lots of papers published in this by our own group. We have published also. And there's also a book on NMR of using chiral compounds. So there is a big book. You can read that. I will share the reference later for you. Right now I don't remember.
Okay, sir.
You can refer. Lots of ways are there. There are so many chiral solvating agents, derivative agents, lanthanide shift agents. Varieties of ways you can do it.
Okay,
But
sir.
it's quite simple. Just you have to have you know that where my molecule can interact. That's all.
That's all.
Okay.
Anybody else? Do you have any? I didn't get your name. Hello. Just now you talked to my
1+.
OnePlus. What is your name?
Sir, Sandeep Pawar, sir.
Oh,
Sandeep
Sandeep Paul
Pawar.
is told me. Correct.
Um,
Okay. Okay, Sandeep, you have any other question? Of course, not to this Sandeep. I'm asking you.
sir. Actually, sir, suppose our compound contain the organometallic compounds, as like the metal group is there, as like this. If you see the structure of the chloroprene, as like the so many compound as like cisplatin, carboplatin. In that the metal is there. So in that there is the any issues for doing the this NMR.
You see, so long as you don't have a metal which is directly bonded to proton, etc., in which case there is what is called night shifts, and there is going to be big problems of shifting of the peaks. And also depending upon whether what is the state of the molecule, whether it is a ferromagnetic state, paramagnetic, and a diamagnetic state. If the molecule exists in a ferromagnetic, let's say ferromagnetism, you will not be able to get NMR spectrum so easily. It will give you a very, very broad spectrum. That depends upon your molecule of your interest. But in so many of our molecules, long back, I have published a couple of papers on organometallics, where we used to get a very good and sharp spectrum. There is no problem at all. Most of the time, we'll get good spectra.
Okay, sir.
So, all right, I think our time is coming. Next session we will start in 15 minutes. So, you have any other questions, Sandeep?
No, sir. थैंक यू सर, आपने बहुत अच्छा मतलब वेरी गुड प्रेजेंट किया और अच्छा ये दिया, तो उसके लिए बहुत बहुत धन्यवाद है सर.
You can okay, Sandeep will talk to me in English. So what did he say?
Yeah,
Sandeep?
he's telling thank you for nice explanation.
Okay, very good. Okay, thank you, Sandeep. I think now
Okay.
time is up. We have to call up because we have another session after 15 minutes. So,
Okay, thank you.
thank
sir.
you. Thank you.
NPTEL person.
Bharat.
Yes, sir.
Yeah, is there any direct landline to contact the office? In fact, other than Maya's mobile phone?
No,
Yeah, there is NPTEL office is there.
I'll provide you the number, sir.
Ah, yes.
But only Guru Rao can help only, not
Yeah, Gururaj Maya is the only person who knows.
Yes,
Guru Raj. So
You
you
have
call
Guru
him
Raj-
on mobile, then ask his landline number if it is
No,
problem.
Gururaj Maya is must be there. His mobile is with all of us.
Yeah, mobile is there. And but somebody else was taking some other team member or
Maybe
something.
yesterday he was busy. You call him now.
Ah, right.
Generally, he answers. He's always, whenever I call him, he will answer.
Oh.
You can call him now.
Ah, right. Okay. I thought there is another somebody else. So there is only one person then.
I think so. In the technical side, he's the one person. I think.
He is the only one person, sir.
Oh, I see. Okay, then it's fine. All right then. Okay.
All right. Okay. We'll meet after 15 minutes.